Hello and welcome to Solved, where we help you solve problems. In this video, we'll be solving an example detailing the thermodynamics of a mixing process. Here's the problem. A stream of hydrocarbon gas at 500 degrees Celsius is cooled by continuously combining it with a stream of light oil in an adiabatic tower. The light oil enters as a liquid at 25 degrees Celsius, while the combined gas exits at 200 degrees Celsius. Determine the molar flow rate ratio of the two inputs to achieve the desired output temperature. Use the following properties given here. Let's go ahead and solve this problem. Here is an illustration of our problem. So we have a mixing tower wherein light oil is introduced at the top of the tower because it's a liquid, it should fall down, and hydrocarbon gas is introduced at the bottom of the tower. Since the hydrocarbon gas is at a higher temperature, the hope is the hydrocarbon gas would go up, it would contact the light oil would vaporize, and that would cool down our hydrocarbon gas, such that our mixture goes out at 200 degrees Celsius. So we have a total of 3 streams here. The first stream is the light oil liquid that is at 25 degrees Celsius. The second stream is your hydrocarbon gas at 500 degrees Celsius. And the third stream is our only output stream, and that is the mixture of the oil gas and the hydrocarbon gas. For this problem, we are required to solve the ratio of the molar flow rates of our inputs. We will call that F1 for our light oil over F2 for our hydrocarbon gas. For this analysis, we would need a combination of the continuity equation and the general energy balance equation to derive our expression for the molar ratio. Let us start with the continuity equation. Our system given here is a steady-state open system. Therefore, our continuity equation would simply be the total molar flow rates going in is equal to the total molar flow rates going out. We can use molar flow rates in our mass balance because there are no chemical reactions happening here. Therefore, the amount of moles is also conserved just as the same as the mass. Therefore, we write that the molar flow rate of stream 1 plus the molar flow rate of stream 2 is equal to the molar flow rate of stream 3. I will be calling that the product stream. We will be able to use this continuity equation in conjunction with the first law of thermodynamics analysis in order to simplify the problem. Let us now write our first law of thermodynamics analysis. The first law of thermodynamics equation for open steady-state systems is written as the summation of the mass flow rates of all of the streams going out times the total energy of the streams going out minus the summation of the streams going in times the total energy of the streams going in is equal to the rate of heat transfer plus the rate of shaft work transfer. There is no shaft work involved in this problem, so that is 0. And we can assume that our tower is adiabatic, meaning that energy is only transferred between the streams, but it's not transferred with the surroundings. For our total energy term, this is typically written as the change in specific enthalpy plus the change in kinetic energy plus the change in potential energy. Now, even though our system is in a tower wherein there is appreciable height difference, there are no given values for the heights of the streams in the tower. Therefore, we can only assume that the change in potential energy is negligibly small. We shall do the same for the change in kinetic energy, and that leaves our total energy change to simply just be equal to the total enthalpy change. Also, for the case of mass flow rate, we can simply substitute that with molar flow rate without issues because again, there are no chemical reactions in this system. Therefore, we can now write our general energy balance equation as the flow rate of the product multiplied by the specific enthalpy of the product minus the molar flow rate of stream 1 times the enthalpy of stream 1 minus the flow rate of stream 2 multiplied by the specific enthalpy of stream 2 that is equal to 0. This is now our simplified energy balance. Now, to further simplify this equation, we will be taking advantage of the fact that if you multiply the molar flow rates with the specific enthalpy, you get the absolute enthalpy. Therefore, the molar flow rate of the product multiplied by the specific enthalpy of the product would give us the total enthalpy of the product, that is capital H3. Now, keep in mind that, again, there are no chemical reactions, and if we assume that the interaction between the hydrocarbon gas and the light oil does not affect the enthalpy, such as the enthalpy of mixing is equal to 0, we can actually write the total enthalpy of the outlet stream in terms of two contributions. the contribution of the oil vapor plus the contribution of the hydrocarbon gas. The contribution of the oil vapor is simply the molar flow rate of oil vapor that is still equal to F1 because again, steady state and there are no chemical reactions multiplied by the specific enthalpy of oil vapor on stream 3. Also, for the second term, this is equal to the molar enthalpy of the second stream, that is the hydrocarbon gas, multiplied by the specific enthalpy of the hydrocarbon gas on the third stream. Again, this interpretation should make sense because we are simply mixing two streams that are not reacting with each other. Therefore, their individual contributions to enthalpy will just be equal to the total enthalpy of the outlet stream. This is especially true because we have assumed that the enthalpy of mixing is equal to 0. That assumption is justified because the light oil and the hydrocarbon gas are both nonpolar, and nonpolar substances would have very, very small values of the enthalpy of mixing. With that assumption and with that interpretation, we can now rewrite our general energy balance as F1 H3 of the oil vapor plus F2 times H3 of the hydrocarbon gas minus F1 H1 minus F2 H2 is equal to 0. Rearranging the terms and factoring out common variables, we now have F1 times H3 of the oil vapor minus H1 is equal to F2 times H2 minus H3 of the hydrocarbon gas. Remember that our required is the molar ratio of the two input streams, that is F1 over F2. We can directly get that from our simplified equation, that is F1 over F2 is equal to H2 minus H3 hydrocarbon gas over H3 oil vapor minus H1. This is now our governing equation for the ratio of the molar flow rates of our inlet streams. All we have to do now is to generate the values of the enthalpies and we can get the ratio. Now let us think about how can we get the values of these enthalpies. Of course, we could always use the equation enthalpy is equal to Cp times delta T. However, these enthalpy terms are absolute enthalpy terms. Therefore, we can only get their values if we establish a value of the reference temperature. Let us first establish our formula for the determination of the enthalpies. In general, we determine an enthalpy as Cp multiplied by the temperature minus a reference temperature. Remember that all enthalpy values are always against a reference temperature. And we can also set our reference temperature here as long as for all of the instances, we will only be using one reference temperature. With that definition, we can now write H1 is equal to Cp of the oil liquid times T1 minus T reference. Remember that our light oil enters the tower as a liquid. Okay? Next, H2 is equal to Cp of the hydrocarbon gas multiplied by T2 minus the reference temperature. Next, H3, the contribution of the oil vapor is equal to Cp of the oil vapor multiplied by T3 minus T reference. In addition, we need to add here the enthalpy of vaporization of the oil because remember that the oil is introduced as a liquid and is therefore vaporized. Therefore, the enthalpy of the oil vapor should include two terms. The first term is for the sensible heat gain and the second is for the latent heat. Okay? This definition of the enthalpy is applicable for the streams that undergoes phase changes. Our final enthalpy is H3 hydrocarbon gas. This is simply Cp of the hydrocarbon gas multiplied by T3 minus the reference temperature. No need to include a latent heat term because the hydrocarbon gas entered as a gas and also exited as a gas. The next question that we should answer is, what should be the value of our reference temperature? The choice of a reference temperature is purely arbitrary and it depends on you. We can actually choose a value of the reference temperature that would severely simplify our solution. For example, if you take a look at H1, we don't have a value of the heat capacity of the oil in the liquid form. What we only have is the heat capacity of the oil in the vapor form. Therefore, we do not want to solve for H1. And how can we not solve for H1? That's simple. We simply set the reference temperature as the same temperature as stream 1. Stream 1 is at 25 degrees Celsius. Therefore, if I set my reference temperature to be equal to 25 degrees Celsius, the delta T in H1 would simply be equal to 0. Therefore, we can say that H1 is equal to 0. That is one less term to worry about. Okay, so we are left with 3 enthalpy terms. Going back, we have earlier derived that our F1 over F2 ratio is equal to H2 minus H3 of the hydrocarbon gas over H3 of the oil vapor minus H1. But since we have determined H1 to be equal to 0, then we have simplified our equation. That is now H2 minus H3 for the hydrocarbon gas over H3 for the oil vapor. We can now substitute our given values, and we can now solve for the value of F1 over F2. In the numerator, we have H2, that is Cp of the hydrocarbon gas, 150 joules per mole per Kelvin, multiplied by T2, 500 degrees Celsius, minus reference temperature of 25 degrees Celsius. No need to convert from degrees Celsius to Kelvin because we are in delta T, and in delta T, the conversions to Kelvin simply cancels out. So this is H2 minus H3 of the hydrocarbon gas, that is the Cp of the hydrocarbon gas, 150 joules per mole per Kelvin, multiplied by T3, that is 200, minus 25 degrees Celsius, the reference temperature. In the denominator, we simply have H3 of the oil vapor. The Cp of the oil vapor is 200 joules per mole per Kelvin, multiplied by T3, 200, minus reference temperature, 25, plus the enthalpy of vaporization of oil, 35,000 joules per mole. Our ratio is 0.643. Our interpretation to this ratio is, as long as the molar flow rates of the light oil and the hydrocarbon gas are kept as 0.643, our product would stay at 200 degrees Celsius. This has profound applications for the design of such systems. If we utilized a different molar flow rate ratio, then the temperature of the output would also be different. This problem shows us the applicability of the general energy balance equation in analyzing an open system that is at steady state. That's it for this video. Thank you for listening and consider this problem solved.